How are we doing? All right. Ready for break? Almost there. Well, then I'm ready for break. So our midterm grades are due on the Monday we actually get back from break. There's not going to be any obviously new big assignments that are due between now and then. So I'm going to enter your midterm grade before break. So whatever your grade is in Moodle currently is what grade will be entered for midterm, just to let you know. Okay. So we do have a test on that Friday we get back. It's on the 28th. So might have a better information, I'll say, about your midterm grade after that exam, but since they're due on the 24th, I don't have a lot of choice but getting something entered. So just to let you know, whatever your current grade is what's going to get entered into for your midterm. So, all right. Any questions at all over anything before we get back into talking about span and start some linear independence stuff today? Things going all right? Everybody's super happy. All right. So we discussed span of a set last time. And remember that the span, scroll back up to the definition here. The span is just the set of all possible linear combinations that you can make using vectors from the set. So we talked about a couple of examples, or at least we did one example last time, about a geometric interpretation of a span. So when we did the set of all linear combinations of 1, 0, 0, and 0, 1, 0 in R3, we noticed that we could get any x coordinate we wanted by doing a constant times that first vector, and we could get any y coordinate that we wanted by doing some other constant times the second vector. When we added, we could get any x-y pair that we wanted, but the z always had to be 0. So geometrically, we ended up with the xy plane. Okay. So let's look at this next example where we've got a set of vectors in P3. Vectors in P3 are just polynomials in P3. We wanted to know what the span of x, x squared, and x cubed looks like. So again, the span says to do all the possible linear combinations of these vectors. So in this case, of these terms, these polynomials. What can you get out of that? Do you get the entire set P3 first off? Can you write every single polynomial of degree 3 or less as a constant times x plus a constant times x squared plus a constant times x cubed? What's missing? The constant terms, right? So verbally then, what set do I end up with? I certainly get polynomials of degree 3 or less, right? But what do I end up with? What has to be true about the polynomial? Say it again. So the graph would go through the origin, so the constant term would have to be 0, right? So this is the set of polynomials of degree 3 or less. Also and including the 0 polynomial. That parenthetical has to be in there because the 0 polynomial has no degree. That have no constant term. Have 0 constant term because it technically has a constant term. The constant term is 0. I can get any x term I want by doing constant times x. I can get any x squared term I want by doing a constant times x squared. Same for the x cubed. You add them together, so I can get anything with an x in it, right? Anything with an x squared, or an x cubed, but I can't get any constant besides 0. And then so, like Declan said, graphically, if you would look at the graph of all of those, it had to be the polynomials of degree 3 or less that pass through the origin. Yes. Yeah, there's not any constant in there that you can add in there. Yeah, that's right. All right. Since we're doing sets of linear combinations of vectors, it turns out that if I just take any non-empty subset of vectors, I always get a subspace. Okay. So just to look at the proof of this theorem, Well, we're assuming that we have a non-empty subset, so it's already non-empty. Again, if we want to show something as a subspace, what do we have to show? There's two things we have to show. Right, yeah, closure under addition, closure under scalar multiplication, right? I have to show those two things. So to start this off, let's let, I'll say W be the set of vectors V1, V2, out to Vn. We'll let that be our non-empty subset. We'll also let S be the span of this W. So it's S that I want to show as a subspace, right? So it's the span of a non-empty subset. So I start with a subset. I'm going to look at the span. So again, when we want to show that it's closed under addition and closed under scalar multiplication, we want to take two vectors out of here, show that the sum is back in there again, and then do the same thing for a scalar times one of them, right? So let's I'll call it, let's call them x1 and x2 be in S. If I'm a vector in S, what does it have to look like? S is defined as a span of things. Span is linear combinations. So if I'm a vector in S, what does X have to look like?
CV1.
Yeah, good. Constant times V1 plus constant times V2 and so on down the line, right? And the same thing for X2. Then X1, I'll say, is equal to C1 V1 plus C2 V2 out to Cn Vn. And I need to use different constants, probably, for X2. So I'll call them D's. And if I could write, that would be helpful. So I know that my constants are real numbers, so I'm writing x1 as a linear combination and x2 as a linear combination. Right? That's all I'm saying with that statement. What do we want to do with these two vectors? Say it again. Add them up. Add them up, right? Add them and show that it's back in S again, correct? So when you add x1 plus x2, what do you get? What's the coefficient going to be on the V1? Yeah, the C1 plus D1. And on the V2, it'll be C2 plus D2, good. And all the way until we get to Cn plus Dn. Notice to be able to write it that way, we are using axioms of a vector space, right? Technically, I would have that whole vector added to that whole sum added to that whole sum. Then we're using commutativity to rewrite it, to put the V1s together, the V2s together, all the way down. Technically, we're using associativity to regroup things and all that as well. And then when you put the C1 and the D1 together and factor it out, we're using another axiom, right? So there's lots of instances of the commutativity axiom, the associativity axiom, and one of the distributivity axioms in there. Okay. You do this as don't even give it a second thought when you add polynomials, right? There's a lot of axioms that go into being able to regroup and combine like terms, essentially. Okay. Is this a linear combination of the vectors from W? Yeah, this is a linear combination, so this is back in W, or not back in W, it's in S. So S is closed under addition. Now take a, don't use a C. I'll use an M. I already have C's being used for something else. I also want to show that it's closed under scalar multiplication. If I take that scalar times the x1, what do you end up with? What's the coefficient on the V1? MC1. That's a V1. What's the coefficient on the V2? MC2. MC hammer? No, that's not it. Then get all the way to MCN. Is that a linear combination of the vectors from W? Yeah. So this is back in S again, right? Again, notice there are several, well, in particular, there's two axioms really being used here. Technically, when you start this, I have M times that whole thing, right? Then I've got to distribute my M to each piece, but my M would be on that. And so then I have to reassociate my scalars. Okay. So I have distributivity axiom, and I have that associativity for scalar multiplication axiom being used. But in particular, it's back in S again. So S is closed under scalar multiplication. So I have that it's a subspace of V. Mm-hmm. How do I know I get to start with this? It tells me it's a non-empty subset. So I just put some vectors in it. It didn't tell me which vectors, which is why I just called them V1 out to Vn, but it tells me it's non-empty, so I know I have vectors in there. Yeah. Other questions on that one? All right. So, why do we care? It's a good question, right? Why do we care? Our goal here, eventually, is to get to the idea of being able to write every single vector in a vector space in terms of just a few vectors. You do that in Calc 3 when you write every vector in R3 as something times I plus something times j plus something times k. You can write everything in R3 as i's, j's, and k's. You only need those three vectors to describe everything. Okay? So in that case, what we're saying is that the I, j, and k span the entire set R3. Okay? So our goal, again, is to get to the point where we can say, I can write every single vector in a vector space in terms of just a few vectors. Okay? Because then I can just play around with those few vectors and do some other things, which makes life a lot easier if I can prove things for the entire vector space just in terms of a few vectors. You do this, again, like I said, in differential equations. When you're trying to solve a differential equation, you're looking for a certain set of functions that you know have to span the entire space of solutions for the differential equation. So you do this stuff regularly in other classes. You just don't use those words necessarily. Okay. All right, so what do we mean by a spanning set? So if I have a subset of vectors in my vector space, I say that it spans the set, or has a spanning set of V, if every vector in V can be written as a linear combination of vectors from S. So writing it in symbols, what we would say is that if W is in V, then there exists C1, C2 out to Cn in R, such that W is equal to C1V1 plus C2V2 out to CNVN. No matter what vector we pick in V, I could write that vector as a linear combination of the vectors from S. That's what that means. Now, again, like I said, we want to be able to do this because if if I need to talk about the entire vector space, I know that I really only need to talk about this particular subset and play with that subset. That's the idea. Pardon me. We hope that this is also unique, and we'll need an extra property for it to be unique and do it exactly one way. And that's where we're headed with everything in this section. All right. So how do I know if something spans? Okay. How do I know if it spans? So what we mean by that is if I want to show that this is a spanning set, this set here, if I want to show that it's a spanning set, I need to show that if my, I'll call it x comma y is in R2, we can find C1 and C2 so that C1 times 1, 1 plus C2 times 2, 3 is equal to x comma y, no matter what the x and y are. That's important, right? If it's going to span R2, it doesn't matter what I start with, I can always do this. That's what that means. If it's going to span R2 or be a spanning set of R2, that means that no matter what I choose to start with, I can always solve this. Okay? What system of equations would pop up if you tried to solve this?
C1 plus 2C2 equals X.
And
C1 plus 3C2 equals Y.
right? That's the system you would solve, right? If you wrote this as a matrix equation, what would the matrix equation look like? 1, 2, 1, 3 times. No. Yeah, we're solving for the C1 and the C2, and then it equals XY. Now, pardon me. If I want to be guaranteed that this is going to always have a solution, what better be true about this matrix that's on the left-hand side? If I want to be guaranteed that it always has a solution, what better be true about that matrix? Invertible. It better be invertible, right? In this particular instance, right? But in particular, if you think about when you row reduce it, when's the only time you could possibly get something that's not solved, that doesn't have a solution? What has to happen if you knew that it didn't have a solution? Oh, you guys have a row of zeros, right? You need to get a row without a pivot. That's the only time that you can get an inconsistency, right? If you get a row that always has if every single row has a pivot when you row reduce, then it'll always have a solution. If you get a row of zeros, then there'll be cases where it doesn't have a solution. So notice here again, we talked about this the other day. Notice here I've got my columns are just the vectors, right? So the process for showing that this is going to be a spanning set is put it in a matrix and row reduce. That sounds familiar, right? So for a spanning set, you're going to do the reduced row echelon form. In this case, if you do your reduced row echelon form, you should get the identity. Not too hard to see. You'll use your calculator. You're not going to do it by hand. Okay. The important part is, since we have a pivot in every row, okay, we see that this system is always consistent. My goodness, if I could write this morning. We see that the system is always consistent. So this means the set spans, or is a spanning set. Oops, spans R2. Is a spanning set of, or just say spans. Good. Yes.
So, you have like infinite solutions. That means it's not consistent.
No, if it has infinite many solutions, it is consistent. But if we get a row of zeros, you can always find a situation that it will be inconsistent, so it doesn't span. If you have a pivot, if you have a row that doesn't have a pivot, you can always find some vector on the right-hand side when you row reduce that would not have a zero in that lower right. It would not have a zero matching up with your row of zeros. It's not saying that some vectors aren't in the span, but if you get a row of zeros, that says that not every vector is in the span, so it can't span. Okay. So we're not saying that we always get it inconsistent. We're just saying that there are scenarios where it is inconsistent. Correct. Correct. It always has to be consistent no matter what. That's why we always have to have a pivot in every row. Okay. For what I mean by that is, for example, if I had, say, the vectors 1, 2, and 2, 4, well, if I take any vector x, y and try to row reduce, notice if I do negative 2 times the first row and add it to the second row, I get a row of zeros, right? Okay. In order for that to be a consistent system, what has to be true? That has to be 0. So my second coordinate has to be 2 times my first. If my second coordinate is not 2 times my first, it's not consistent. That's what I mean, that it has to be consistent no matter what. There are scenarios for this to be consistent, but it's not consistent in every single scenario. Okay. So when we row reduce, we have to have a row. Every single row has to have a pivot. That's the important part. Yes. Say that again. It depends on how many vectors you have. That's going to be the next piece that we talk about. We're going to get there. Okay. For spanning set, it doesn't have to be unique. There could be infinitely many. Okay. All right, let's look at this next example. We want to show that this is a spanning set for P3, or excuse me, for P2. Same idea here. If I take any arbitrary polynomial I want to solve this equation. Oh, C's a bad letter. I use a D there, since I used C's on my constants on the other side. This is what we would need to solve, right? If I want to show that it's a spanning set, no matter what you pick on the right-hand side, I can always find constants to use on the left-hand side. That's what you have to solve. Is it going to be a spanning set? What has to be true if this is going to be true? What system of equations can you set up?
C1 plus C2 plus C3 plus A.
Okay. And?
C2 plus C3 plus B.
Good. And?
C3 plus D.
Good. That has to be true, right? No, and again, no matter what we pick for A, B, and D, correct? Notice again, if I set up my matrix equation, it would look like, oops, that. That's what it would look like for my matrix equation, right? Again, in order for this to have a solution no matter what, since it's squared, that would be invertible, but in particular, I would need a pivot in every row when I row reduce. When I row reduce this, am I gonna get a pivot in every row? Yeah, they're already there, right? Now, notice again, look at your columns of your matrix and look at the original vectors. Do you notice any relationship between the columns of your matrix and the original vectors? The columns are the coefficients. Yeah, that's exactly right. 1, 1, and no x's and no x squares. 1, 1, 1x, no x squares. 1, 1, 1x, 1x squared. That's exactly what they are. Yeah. And notice they have been put vertically into columns. Isn't that what we did in the previous example? Yeah. Starting to see a shortcut? Yeah. All right, so again, if we row reduce, we see a pivot in every row, so it'll be a spanning set. Okay. What about the next example? What do you think we should? Yeah, go ahead.
So if it's not row reduced, we can't get every pivot in every row. That means it's not a spanning set.
Correct. That's exactly right. Yep. If we don't get a pivot in every row, it's not a spanning set. Yep. That's exactly right.
Go to setting up the matrix.
Yeah, that's exactly right. Yep. That's exactly what we're going to do. So what do you think we should do here? Instead of our matrix, good.
1, 0, 0.
Down.
Going
down. Good.
0, 1.
Good. That's it. What do you get when you row reduce that matrix? What matrix do you get? That one. That is the reduced row echelon form of that matrix, right? Do I have a pivot in every row? No. There's no pivot in row 3. So it's not a spanning set.
So can you just skip this step when solving a spanning set and just skip to put in?
Yeah, absolutely. Yep. No, you don't have to do all the other stuff either. This is how you're going to do it every single time. Yeah. We're always going to put them in columns. Okay. Can you tell me a vector that is not in the span? Can you tell me a vector in R3 that you cannot write as a linear combination of 1, 0, 0, 0, 1, 0? 0, 0, 1. Yeah, exactly. That would make it inconsistent. Yeah, that's exactly right. There is no way to get a 1 in the third component by using those two vectors. All right. So again, here the idea is how can we tell whether it's a subset? We're going to put our vectors, whatever they happen to be, in a matrix as columns and row reduce. If there is a pivot in every row, then the set of vectors, I'll just say the subset, spans V. And again, the why do we care part, this means we can express every vector of V in terms of a finite number of vectors. That's the idea. not just some, but every single vector in my vector space can be described in terms of a finite number of vectors. That's the whole goal here. Because then I'm going to be able to do things on the entire space by just worrying about a few vectors. It's really going to be important when we talk about linear transformations later. We can know exactly what a function does to every single vector in my space if I know what the function does to a finite set of vectors. That's one of the reasons why we care. You do this in Calc 3, for example, when you write every single thing in terms of an I and a J and a K, right? And then you play with the I, J's, and K's. It's the same concept. All right. So using this knowledge, we want to determine whether or not this thing spans R4. So our first step is what? Put in a matrix. So I put my 1, 2, 3, 4 down the first column, my 0, 2, 5, 1 down my second column, my 3, 0, 0, 6 down my third column. Do I really need to row reduce? Or can you just answer the question? What's going to happen no matter what when you row reduce? What do you have to have? A row of zeros, right? Because when you get your pivots, you get a pivot in column 1, and then you get a pivot in column 2, but it can't be in row 1, so it has to go down a row. Do the same thing in column 3, you're going to run out of rows, right? So we have more rows than columns. So we must get a row, at least one row, of zeros when we row reduce. We have to. We don't have a choice. We run out of rows. Yes?
Well, the last row doesn't have that one.
We won't. There won't be a 1 when we row reduce. It's impossible. Because we would get a 1 here, and then we would get a 1 here, and then you would get a 1 here. You run out of spots. There has to be, because what is your steps in row reduction? You get a 1 here. What are all those? Yeah, those are all zeros. And you get a 1 here, and then zeros, right? We're going to run out of room. Yep, that's the idea. Yep, we're going to run out of room. Okay. So it's not possible. The set does not span R4. Okay. So if you run out of room, you know automatically that it's not going to span. Okay. Now let's go the other way. Let's look at this one. Same idea. Let's make my matrix. I'm going to put each of these vectors as columns. It doesn't matter how you do it as long as you're consistent as you move from left to right. Okay. What I mean by that is I could do 1, -2, 0, 5. Notice I went row and then column. Do that for every single matrix past that. So 6, 1, 3, 0, -2, 0, 1, 1, 0, 3, -1, 4, 1, 1, 1, 1. Right? You could have also did 1, 0, -2, 5. Right? Could have also done. Bad grammar, sorry. 1, 0, -2, 5. You could have done that. But then if you do it that way, then this has to be 6, 3, 1, 0. Just keep it consistent all the way down. Okay? All right. Now, just because, now am I going to run out of rows first off? Am I going to run out of rows when I row reduce? No. All right. So, looking at this, we said that we won't run out of space, so we can get a pivot in every row, but are we guaranteed? No. So you actually do need to row reduce this one. Anybody type it in and row reduce it?
1, 0, 0, 0, -126. 126. 1 over.
Oh, 1/26th. Sorry.
0, 0, 1, 0, 0, 15 over 52.
Okay.
0, 0, 1, 0, 9 over 26. 0, 0, 0, 1, 11 over 52.
Okay. The important part is pivot in every row, right? So since we have a pivot in every row, this is a spanning set. That was the important part. Since we have a pivot in every row, it spans. Okay. That process okay? Yes.
Oh, we have to figure out the column zeros.
That's okay. Column of zeros is fine. It's the rows that matter for span. That's a good question for what we're going to do next. But for span, doesn't matter. We just want to pivot in every row. You'd have to have, when you set up your matrix to get a column that's all zeros, you would have to have zeros all the way down that column to start with. So you'd actually have to have zeros missing somewhere. In particular, you'd have to have the zero vector in your set, that's kind of worthless. Okay. Same idea on this one. Again, same idea. Set up your matrix. What would go in the first column of your matrix here?
1, 1,
Okay. And your second column?
-1, -1, 2.
Everybody has 0 in my x term, right? Because there's an x term that's missing, yes? Yeah, so -1 and then 2. Make sure that you zero fill, right? Notice that we've got an x here. That means I have to have an x in the same spot, right? We want to keep everything consistent. Next column would be
-2, -1, 1, 1.
good. And the final column would be
0, 1, -3.
good. Again, just by looking, can it be a spanning set? Yes. Is it guaranteed to be a spanning set? No. You actually have to do the row reduction on this one. But again, for the love of all that is holy, please use your calculator. You'll be taking forever to try to row reduce these by hand. By the way, if it's going to be a spanning set, what matrix do you need to see when you row reduce? In this case, I better see the identity, right? It's a 4x4. Do you see the identity? Now, what do you get?
1, 0, -1. 0, 1, 1, 1.
And then the rest are zeros. Good. Okay. So again, in particular, those two rows have zeros, right? So this is not a spanning set. Yes.
Would you pretty much say about since it's a 4x4 matrix?
It has to be the identity. If it's going to span, it has to be the identity because we have to have a pivot in every row.
Anytime you say matrices, they all give us identity matrix.
If it's going to span, it will. If it's going to span, because the only way you can get a pivot in every row is if you get a pivot in every column. In that case. All right. Other questions on that? All right, so let's move over to slightly different concept, but related. We're going to talk about linear independence. So again, we have a non-empty subset of V. The idea here is we want them to be linearly independent. So the idea here is when I hear linear, I think linear combination from an algebraic standpoint. Okay? If it's going to be linearly independent, that means that I can't write any vector in the set as a linear combination of other vectors in the set. Okay? That's what it means to be linearly independent. So what that means is that V1 actually needs to add additional information, right? If I can write V1 in terms of the V2 out of Vn, then why did I put it in there? Right? Same idea with the V2. It better actually add information. An equivalent way to say something is linearly independent is that if I can write the zero vector as a linear combination, this needs to be equal to 0, then all of my constants must have started to be 0 to begin with. Linearly independent means the only linear combination that gives you the 0 vector is to use zeros for your coefficients. Okay? If I have something that's not 0, say C1 is not 0, then I could move everything over to the other side and divide by C1, and I have my V1 as a linear combination of the other vectors. I don't need it. Okay. That's the idea. All right, so let's see how we show something is linearly independent. Let's look at this set. Now, let me ask you a question. Is it possible for that set to span M22? Just by what we talked about earlier. Can that set, without doing any work at all, can that set span M22? No. Because again, if I make my matrix, when I make my matrix to row reduce, what would be the dimensions of the matrix? 4 by 3. I run out of rows when I row reduce, right? So this can't possibly span. It's impossible, right? Okay. This is another concept we're going to come back to later as well. Okay. There's not enough vectors in there. Yes. No, it's just I'm just asking you to review that part. Yeah. Okay. There will be cases where there one tells you the other and vice versa. But in this case, I know it cannot span. I don't know about linear independence yet. But go ahead. Correct. It never spans if you have more rows than columns. That's exactly right. Yep. Okay. All right. So linear independent is the same idea, right? I still have this linear combination, right? So in this case, I can do the exact same thing like I did when I started my spanning thing. Make your matrix with columns. Now, I'm going to put it in here, but don't write it down. I'm going to put it in here to start with. Don't write it down because it doesn't matter when you row reduce. Remember, I'm trying to get a linear combination that gives me the 0 vector. So really, I would be augmenting a thing of zeros, right? Because, again, think about it. I would want C1 times 1 plus C2 times -3 plus C3 times 5 to equal the 0 vector, so I have a 0 on the right-hand side, right? And so on down the line. Does this column matter at all when you row reduce? No. Okay. All right. So I don't really need it. However, you do need to put it in there if you're going to row reduce on your calculators because it doesn't like it when you have more rows than columns. Okay. But the same idea here, we're going to row reduce. Right? What do you get when you row reduce this one? You will need to put a column of zeros in there and get it to work and just ignore it. I know for certain you'll get a row of zeros at the bottom. Yeah.
So that means like putting in the calculator,
Mm-hmm.
if the columns are more than equal to something, but the other way is
The other way you have to zero fill until you get to a square matrix, yeah, because otherwise it won't reduce it for whatever algorithm it uses. What do you get?
0, 1.
Okay.
0, 1, -3 halves.
Okay, and then zeros, yep. Okay, cool. All right. So, is this linearly independent? Now, let's think about it. Linear independence, by definition, says there is exactly one way to write the zero vector, right? How many solutions does this system have? Infinitely many. So is there exactly one way to write the zero vector? No. There are infinitely many ways to write the zero vector, right? So this here tells us that we have infinitely many solutions. So it's not, the set is not linearly independent. We would write linearly dependent. What's missing in that column? What's missing in the column to give us infinitely many solutions? What doesn't that column have when you row reduce? A pivot, right? Right? So think about what we did for span. For span, we row reduced. For it to span, we had to have a pivot in every row. For linear independence, where do you think you need a pivot? Every column. Good. Exactly right. So let's see if we can should have another example here. No, maybe not. We go down. Is there another example in here? Let's go, since I only have a few minutes and I don't want to write all the concepts down, we'll talk about it on Friday. Let's look at these examples. It was a page or two past. Okay. Let's look at a couple of these examples here. In particular, let's look at the second one. What would your matrix look like after you put your vectors in columns? What would your matrix look like? What's the first column? 3, -1. What's the second column? 4, 5. What's the third column? -4, 7. Now, thinking for linearly independent, you just told me you have to have a pivot in every column. Is that even possible without even row reducing it? No, I don't have enough rows to do that, right? So we can't get a pivot in every column when we row reduce. So it can't be linearly independent. Could it still span? Yes. But if I know I have too many columns, it can't be linearly independent, but it could span. Looking at the next one, let's not even write the matrix down. Tell me which one it can't be automatically. Can't span or can't be linearly independent? Can't span, right? Because if I were to write the matrix down, it'd be a 3x2, right? There's not enough columns. Can't span, could be linearly independent. And again, we're going to come back to that concept next time. All right? So have a good one. We'll finish this up and we'll also do section 4.5 on Friday. We'll see you then.